Hello everyone, I am Professor Anish Vora and I welcome you all in this video lecture. In this video lecture, we will study about different types of semiconductors. Let us start with the classification of semiconductor. Semiconductor is broadly classified into two categories. That is intrinsic semiconductor and extrinsic semiconductor. Again, extrinsic type of semiconductor is divided into two categories, that is p-type semiconductor and n-type semiconductor. Now let us understand what exactly we mean by intrinsic type of semiconductor. Intrinsic semiconductor is pure semiconductor without any impurity. The amount of impurity level is less than 1 part in 10 raised to 8 power. Then that semiconductor is known as the intrinsic semiconductor. Meaning this impurity is very less, negligibly small, and it is considered as a pure semiconductor. Then that type of semiconductor is known as an intrinsic semiconductor material. Same way, extrinsic. When in pure germanium or silicon, impurity of the element is added in very small definite proportion, then it is known as an extrinsic semiconductor. And then doping. The process of adding impurity element in pure semiconductor is known as a doping. Now let us understand what exactly we mean by n-type of semiconductor. When in pure germanium or silicon, the impurity of the pentavalent type of element is added, for example phosphorus, arsenic or antimony, in very small definite proportion, n-type semiconductor results. We have one pentavalent element like antimony is added as an impurity with silicon or germanium atoms. All other neighboring atoms are of silicon or germanium. We know that antimony, that is a pentavalent element, and it has 5 valence electrons in the valence band. So covalent bond is generated between valence electrons of the antimony as well as the valence electrons of the neighboring silicon atoms. And the remaining germanium or silicon atoms make a covalent bond with 4 valence electrons of each. We know that antimony has 5 valence electrons. Out of this, 4 valence electrons have made covalent bond with the valence electrons of the silicon atoms. But 1 electron remain free, which do not have any covalent bond with any of the valence electrons of the silicon. Again, it is away from the nucleus and it is bounded with the nucleus with very less force of attraction. In that condition, it is very easy to detach this electron from the nucleus and made it free electron. This is free electron, and the energy required to make it free electron is very less. Even at room temperature, the heat energy is imparted and electron can be made as a free electron. For example, 0.02 electron volt is required for germanium and 0.05 electron volt is required for silicon. This way, free electron is generated with the added pentavalent impurity in the pure germanium or silicon semiconductor. The number of free electrons are exactly equal to the atoms of the impurity added with the pure germanium or silicon. This impurity is called donor impurity element because they are donating the electrons. Donated electrons are known as excess electrons. Majority charge carrier in case of N type of semiconductor material, that is electrons. Electrons are produced and act as a charge carriers. As temperature goes on, more covalent bond breaks and large number of electrons and less number of holes are generated. Hence, electrons are the majority charge carrier in N type of semiconductors. Then P type of semiconductor. When in pure germanium or silicon, the impurity of the trivalent element, for example gallium, indium, is added in very small definite proportion, P-type semiconductor results. One atom of gallium is added as a trivalent impurity element in pure germanium or silicon. So gallium has 3 valence electrons in its valence band or outermost orbit. So it is making covalent bond with other 3 valence electrons of the silicon or germanium. So all other silicon atoms have 4 valence electrons, and as usual they are making covalent bond with neighboring silicon or germanium atoms. But 1 valence electrons of silicon remain without covalent bond. This deficiency of 1 valence electrons, that is because of gallium, because it has only 3 valence electrons in its outermost orbit. But now this incomplete bond or the position vacant for the valence electrons can be fulfilled with the neighboring valence electron from the silicon. And the heat energy required is very less, that is hardly 0.01 electron volt, and at room temperature also the heat energy can be imparted to make it possible. When heat energy at room temperature is imparted, one of the neighboring silicon atom will lose one of the electrons and it will be shared with the incomplete covalent bond made with the gallium. So one electrons is shared and the covalent bond is completed. But the position remain vacant when electrons leave the covalent bond of the silicon atom, and it is known as a hole. The hole is generated, the net charge of the silicon atom is positive. Same way, in case of gallium, after addition of 1 additional electrons, it is a negative. So in P-type semiconductor material, this way holes are generated, holes are charge carrier, and gallium atom is with negative charge, it becomes immobile. This impurity is called acceptor impurity element because they are accepting the electrons from the neighboring silicon atoms. Majority charge carriers. Holes are produced and act as a charge carrier in P-type of semiconductor material. As temperature increase and some more covalent bonds are broken, large number of holes and less electrons are generated. Hence, holes are the majority charge carrier in P type of semiconductor material and electrons are the minority charge carrier. Thank you very much for watching my video. Keep watching. Thank you very much.